Welcome everyone for the fourth session of this ISSS course, Introduction to Astronomy and Astrophysics. Today we will start the second module, or the module which I named in 4. That is the fourth module in this course. And today there will be the first lecture of the fourth module. And this class we will cover some basic physics lesson. Those will be a recap of our 12th grade or the BSc level physics lessons. So we can now start the session. Insert slide. Start show. Okay. So today the lecture will be of the recap of the physics lesson. So until now we have covered one module, that is the where I covered ancient to modern astronomy, the evolution of the astronomy. So the in ancient time the astronomy, you can tell this, that were mainly on the celestial mechanics, and in the modern days the astronomy is mainly multi-passenger astronomy. So in the early days people were more interested in the celestial mechanics, that is how the planets or the stars move in the sky. But now we are mainly focused on detection of the signal from the different cosmic sources. We are mainly focusing on those the sources those are sending us signal, and we want to know why these sources are sending us such signal. So broadly, modern astronomy can be divided in the 4 sub branch. One is observational astronomy, another is the planetary science, or astrophysics and cosmology, where people study the extragalactic astronomy, and another part is mainly more linked with the astronomy and the biology, that is the astrobiology. So for the people who study the observational astronomy, they observe the celestial object using telescope and the other apparatus. So for the observational astronomy people, they observe mainly they can observe extragalactic sources or the galactic sources. They design telescope, improve the telescope design uh, for more detailed understanding of universe. And for the planetary science, mainly study the planets in the solar system, how the planets formed, what is the atmosphere of the planets, how the weather pattern changes in the planet, etc. And the astrophysics and the cosmology, that domain, people deals with the physics of the universe, properties of different objects, birth and evolution, and the fate of the universe. In the astrobiology, people studies the origin and the evolution of life in this universe. So the astrobiologists are mainly interested in why the earth in the earth or in the universe or in the earth the life came, why we exist. The main question the astrobiologist asks this. So in the astronomy, before going to today's lecture, we will have some we want to have some feel of astronomy, or the feel of the course we are studying. So you can think of the sky as a laboratory, where which give you some conditions, or the very vast amount of conditions that we cannot produce in the earth. So there is in the sky there is objects which have temperature about 10 to the power 10 Kelvin, also have the very low temperature objects in the sky. So this sky signal gives us opportunity to study about different state of matter. So the in the universe there is the experiments are going on every microsecond, micromillion second, or the every pinch of second. So we ourselves are doing no experiment here. We ourselves do not do any experiment here. Processor itself occurring in the universe. We have just some telescopes. We are detecting those signal. So now from this detected signal, we have to figure out what process happened in the sky so that we are getting this signal. So you can think this like a detective story where some incident has happened. That incident have some clues or evidences. So now you are dealing with those evidences, and from this evidences you have to figure out what crime, what sin was happened there. So you can think astrophysics as such kind of detective story. So you are getting the vast amount of as in the modern days you have the telescopes have been improved. The resolution of the telescope has been improved. We have seen in the Gaia mission and the Hibiscus mission the data volume how get increased nowadays. So now for this it is missions, we are detecting vast amount of data. So data science has become the integral part of astronomy and astrophysics since 2000s era. Now the astronomy is the one of the mainly most linked branch with the fundamental physics, because astrophysical system in the astrophysics can give us different kind of system, such as some three body systems, accretion disk system, etc. Also different kind of matter, different state of matter can be in the universe. So astrophysics is a one of the fundamental is closely linked with the fundamental physics. And also for doing astrophysics in this current era, you have to rely on the data science techniques as well. Now today our class will be a recap of the 12th grade or the BSc level study. So the light is mainly the light or the photons are reading message from the cosmos. We know what is light. Light is an electromagnetic wave. Light has both two type of property, such as the light has wave property and also light has a particle property. Light becomes visible when it strikes with an object surface, and when it strikes with an object surface, some light gets reflected, some light gets refracted, or gets transmitted within that object. Uh, so we are seeing some reflected light. We see some reflected light from the object. An observer sees color when some wavelengths of light are reflected by the surface of object, but others are absorbed. Light can also become visible when it is refracted by an object. A rainbow is produced by the refracted light. Light wave light is electromagnetic wave. So it has both two kind of fields, such as the electromagnetic field, electric field, and the magnetic field, E and the B. And this both electric field and the magnetic field are perpendicular to each other, and the light propagates on the perpendicular direction to E and B field, that is E cross B's direction. The light gets propagated. Light interacts with charged particle through the interaction of the electric and the magnetic field. We all know what is the speed of light, that is the 3 into 10 to the power 8 meter per second, or 300,000 kilometer per second. So the frequency tells us, so light is often shown as a wave kind of thing. So frequency tell us how many times any point on the rope bops up and down in within each second. And the wavelength is the distance between the adjacent peak. Peak to peak distance is the wavelength, or peak to peak distance is the wavelength. and the frequency is the number of times each second that the electric field peaks at a point. Now we just shown that the light interacts with matter. There are different ways that the light can interact with matter. One way is the emission, one way is absorption, and another way is transmission. So there are, first we have to consider the absorption, where suppose there is some source of light or there is incident radiation. This radiation is falling within this surface. Suppose some part of it gets reflected, some part of it gets reflected, some part of it gets transmitted, that is going out, uh, transmitted, that is the directly goes out and then comes from the comes outside from the other surface. And there is some part of light that is get absorbed within this matter, and there is some part of light that goes into matter but it changed path, that is refracted. So also this matter can emit give off light, that process is known as emission process. And absorption, the process we told that the light get absorbed does not come out from the other surface or any other surface. The transmission of object, the transparent object transmit light, that is the suppose some light or radiation is going to this within this object, and it is just getting out from that object. So that process is transmission. And another process is the reflection, what we call the light strikes into the surface of the matter, and it get ready just gets scatter it changes direction. So the reflection and the reflection or the scattering is the interactions between light and matter which determines the appearance of everything around us. So while we are called the scattering of light, we have to figure out the scattering cross section. We have to figure out the scattering cross section, or that is determined by the objects which are taking part in scattering. So if the light's wavelength is very greater than the radius, the 2 pi r, r is the radius of the object, then the scattering, what happens, we call that Rayleigh scattering. And the geometric scattering is when the light which is falling on the matter or atom, that's wavelength is very much smaller than the 2 pi r, then that scattering is called the geometric scattering. Here is the other thing. So what is matter? Matter is composed of very tiny element known as atoms. Atoms consist of the nucleus and orbiting electrons. We know in the matter electrons orbit in different energy level. The nucleus we know composed of the protons and neutrons. So and matter has the length scale of 1 angstrom. An atom is often denoted by the atomic number, is always denoted by atomic number and the mass number. Atomic number is number of protons in the nucleus, and the atomic mass number is number of proton plus neutron. Atomic terminology, the atom, there is ion and isotope and molecule. 3 type of terminology comes under atom. Ion is an atom with more and less number of electrons than proton. Isotope is an atom where the same number of protons in the atom but different number of neutrons, such as helium 4 and helium 3 are the 2 isotopes of helium. Both this has 2 protons in its nucleus, but helium 4 has 2 neutron and helium 3 has 1 neutron. And isotope, there are also different isotope for carbon. Carbon 14 which is a radioisotope, carbon 13, and carbon 12. Carbon 12 isotope, a different isotope is present in different proportion in the earth. So in the earth, carbon 12 is the main isotope. Carbon 12 is the main isotope. It consists a large about uh, I have to check that the large portion of the carbon is in the carbon 12 form. And also there are molecules that are consist of two or more than atoms, that are the H2O, CO2. H2O consists of two oxygen atom and one hydrogen atom. Sorry, two hydrogen atom and one oxygen atom. And carbon dioxide consists of one carbon and two oxygen atom. So as we told, the electrons have different energy levels. So electrons and of atoms are restricted in different energy level. The energy electrons cannot stay in between two energy level. So if there is some photon is falling on the atom, and if that photon is same energy with any of the energy levels difference, then only the electron can absorb that photon and go to the higher energy level. Otherwise electrons cannot change the energy level. Electrons can change energy levels only by absorbing a photon or emitting a photon. So absorbing a photon and emitting a photon. Now we can consider what are the phases of matter. We know the phases of substances depend on both temperature and the pressure. So in the earth we are getting four kind of phase of matter. One is solid, one is liquid, and another is gas, and another is plasma. So ice is the solid, water is the liquid, and the water vapor is the gaseous phase. Phases of the same material behave differently because the temperature difference is there, and different chemical bonds are present within different phases of matter. So now you can see how the phases of water changes. First is ice. This is the lowest temperature. Then few hundred Kelvin. This up to few hundred Kelvin. It is in the form of normal water. And then in the field after 100 greater than 100 Kelvin, it is going to produce the steam. And 1000 of Kelvin and the million of Kelvin, it is going to the plasma state. Phase change. So phase change for the phase change we have to keep mind that there are 3 or 4 processes of phase change. That is the ionization, that is the stripping of electron changing atom into plasma. Dissociation, making of the molecular bonds, molecules or bonds into molecular bonds and producing atom. Evaporation, breaking of the flexible chemical bonds and changing liquid to the gas. And melting is the breaking of rigid chemical bonds and changing the solid to liquid. Now, today we have to once again check what is the luminosity and the apparent brightness and the inverse square law of light. So as we know, the luminosity is the total number of light or energy star emit per unit second, and the brightness is the light that reaches to us energy per second per unit square meter. So suppose suppose here is the star and you are sitting here on the earth. So luminosity is the total amount of power, that is energy emitted per unit second from the star, and this energy is radiated within the whole space, and you are detecting the you are detecting a brightness sitting on earth. So apparent brightness is the amount of starlight that is reaching to earth, and the area of the sphere. From the area you can plot the sphere of different area radius around this object, and in one such sphere, your location is falling. So area of the each sphere is equal to 4 pi, the total area of each sphere surrounding the object is 4 pi into distance or the radius is square. Light passes through the each sphere is the same, and we have to divide luminosity by area to get the brightness. Brightness decreases as we travel from the center to the outer region. So from this figure one can write the relationship between the brightness and the luminosity. So brightness equals to luminosity by 4 pi distance square. We can determine a star's luminosity if we know the distance and the brightness. Also vice versa, if you know how the bright the star is and what is the luminosity of the star, then you can get back that to the distance by this formula. Luminance equals to root over of luminosity by 4 pi into brightness. Now from this simple mathematical description or the simple description, you can check what is the photometry. This photometry was early 150 BCE started, and this Greek astronomer Hipparchus devised a system to classify stars according to their brightness. So he on the sky he found that the all stars are not all the stars are not bright give same brightness. So he marked some brightest star with the 1 magnitude and faintest star with the 6 magnitude. He was the first person who developed a photometric scale. In the modern system, his scales is revised to the logarithmic scale, where a difference of 5 magnitude is equals to 100 times intensity difference. So the basic formula we write, the brightness ratio is equals to 2.5 to the power magnitude difference. And the apparent brightness, we will get back to this formula again and again. So in the modern system, the difference in the 5 magnitude is equals to 100 times intensity difference. So difference in the 1 magnitude is 5th power root of 100 is to 1, that is 2.5 is to 2.5 is to 1 intensity difference. So the basic formula is the brightness ratio is equals to 2.5 to the power magnitude difference. So the apparent magnitude measures how bright a star appears from Earth. From the Earth, we take the Vega brightness is equals to 0, and this Sirius has the brightness of minus 1.4. Venus is brightness of minus 5, whereas Moon has brightness of minus 30, and the Sun is very bright, that is it has brightness of minus 2.6. And in the sky, the fainter object have the brightness scale of in the positive scale brightness. That is, the brightest quasar has the brightness of about 12 or something, and the faintest object has the brightness of 26, 27, that range. So first magnitude star is 2.5 times brighter than the second magnitude star, and 2.5 square, that is the 6.31 times brighter than the third magnitude star, and 2.5 to the power 4, that is 40 times brighter than the fifth magnitude star, and about 2.5 to the power 5, that is 100 times brighter than a sixth magnitude star. So in the previous plot or the previous scale what we shown, the Vega has magnitude of 0 magnitude, the Sirius has magnitude minus 1.46, and the Sun has magnitude of minus 26.81. And in the human eye, we can visible stars up to magnitude plus 26, and the faintest galaxy that has been detected has magnitude 29. So, what is the magnitude scale really measuring? The radiant flux, radiant or the radiant energy flux, that is the energy arcs per second per centimeter square, that is coming from the star or any object and hitting your detector, is measured by this magnitude scale. We can define the it mathematically, where with the f1 and the f2 as the magnitude as the flux from object 1 and the object 2. So flux f2 by f1 is equals to 100 to the power m1 minus m2 by 5. So there, if there are two object 1 and 2, they have flux f1 and the f2, and their apparent magnitude is measured as m1 and the m2. So this formula give you estimation of how of the relationship between flux and the magnitude. We will once again come to this in the next class. Now we can check what is the luminosity. So luminosity is equals to sigma t to the power 4 into 4 pi r square, where r is the surface of the star or this object. So for the sun, there is so from the black body emission, the luminosity is proportional to the fourth power of temperature. So we know the sun has 6000 Kelvin, and if it has luminosity 1, if a star is 12,000 Kelvin, that is the 2 times larger than the sun, then it will have luminosity into 2 to the power 4 times bigger luminosity than sun. That is about 16 times luminosity than sun. And if a object has the temperature of 2000 Kelvin, that is 3 times smaller radius than 3 times smaller radius than sun, it will have 3 to the power 4, that is 81 times smaller luminosity than sun. And also luminosity is proportional to the surface area of the object, or the how big one object is. So if a object has the radius of the one solar radius, and if it is sending you 100 photons, then if an object is of two solar radius, then it will send you 400 photons per unit time. So until now we know that the luminosity has depend on both two properties of a source, that is the temperature of the source and the surface area of the source. Now it comes to absolute magnitude. Absolute magnitude is equals to apparent magnitude if a star was placed at the 10 parsec away. Suppose there is you are detecting a star, and this is the real distance from the star. Star is very big. It is greater than suppose it is greater than 10 parsec. So now if you place the star at the 10 parsec away from you, the apparent magnitude that will be visible is equals to absolute magnitude. So luminosity is the total output of the star per unit second. Luminosity depends on the two factor of the source. One is the temperature, that within the Stephen Boltzmann law, and another is the size of object or the surface area of object, which is denoted by the radius of the object itself. And the distance modulus formula, that is the absolute magnitude and the apparent magnitude, from the absolute magnitude and the apparent magnitude is given as this, and from this formula you can get the distance of the object. So absolute magnitude and the apparent magnitude, if there is some object, there is same source, one this has two magnitude at different distances. If you place the same source at different distances, then the apparent magnitude varies. So from that you can measure the apparent magnitude, and you can carry out the apparent magnitude and the absolute magnitude formula. Here I will skip this today. So now I will come to this example letter. So now, what is a spectrum? Suppose you take light, and spectrum is a spectrum we get when we break light through prism. So we take the light and break it into different colors by pressing it to prism or the diffraction grating, and we get spectra, get different color, that is a different wavelength, or we produce spectrum. So light have wavelength beyond, we know light has wavelength beyond the visible band. So there is optical spectroscopy, UV spectroscopy, infrared spectroscopy. All kind of spectroscopy can be done fundamentally and of course experimentally. Now in this course, in this lecture, for the spectrum, we will first mainly see understand there is an optical spectrum. Now there is continuous spectrum, emission line spectrum, and absorption line spectrum. There are three types of spectrum. So this spectrum, what is a continuous type spectrum? Suppose you have a hot light source, and you are the light source is emitting some light, of course emitting some light, and you are placing one prism in front of that source, and the light get diffracted by the prism and create the spectrum. The spectrum of a incandescent light bulb spans all the visible wavelength without interruption. And if there is a hot cloud of gas other than this hot light bulb, and this you just keep a prism before this hot cloud of gas, then the hot cloud of gas only emit light only as some specific wavelengths that depends on the composition of gas itself and the temperature of the gas, and produce this kind of line spectrum known as the this line spectrum or the emission line spectrum you can get from the hot cloud of gas. And if there is some it is another type of spectrum, that is the absorption line spectrum, when there is a source of light and above there is you place a cool cloud of gas. So this hot light will be passing through this cloud of gas, and then some part of this hot light will be get absorbed. So a cool cloud of gas between us and the light bulb can absorb light at the specific wavelength, and this specific wavelength of course depend on the composition of the cloud of gas. And when we are get disperse this light through the prism, we get the dark absorption line in the spectrum of the hot light source. So there you are getting three types of spectra. The detailed spectra illustrating Kirchhoff's law. So the one incandescent light bulb, when you are passing this within the prism, we are getting the continuous spectrum. This is a smooth continuous rainbow of light. This intensity varies varies slightly at the different wavelength. Of course, you can see there is a black body type spectra. Intensity varies slightly at different wavelength. And emission line spectra, when a cloud, the hot cloud emit its own light, but only at the specific wavelength determines its composition. We see bright emission lines at the specific wavelengths but no other light. So you can see this spike at the each emission lines. And another kind of spectra that we discussed is the absorption line spectra. That is when there is a bulb and there is a you are placing a cold gas cloud before the bulb, and after that you are placing a prism. So the light coming from this light bulb getting absorbed by this cold glass cloud, and then the light those light remain those wavelength remain, get passed through the prism and get dispersed. We see the dark absorption line where cloud has absorbed lights at the specific wavelengths. So the cloud absorbs light at the specific wavelength. Those wavelength gets determined by the energy level of the cold gas. So now, how does the light tell us about the composition of object? So for the composition of the object, there is energy level transition, and the only allowed changes in the energy are those corresponds to a transition between electronic energy level. In the atom, there are different energy levels we showed or we know. There are in the lower energy level is the ground level, upper energy level at the excited level. So when electron comes from upper energy level to lower energy level, it emits photon, and when the electrons absorb some energy packet from the photon some energy packet, it goes up. So only allowed changes in energy, those are corresponding to the transition between electron energy level happens. Here is a spectrum of the sun. You can see here some absorption within the continuous spectra. There are absorption lines in the sun spectra. So this absorption line tells us about the compositions of sun's photosphere, or the elements those are present in the sun's within the sun. Each type of atom has an unique set of energy levels. Here is the hydrogen. Here is the hydrogen, and the energy levels of hydrogen has been shown. Each transition corresponds to a unique photon energy, gives a photon with unique wavelength and frequency. So each type of atom has a unique spectral fingerprint we just shown. Specific lines, specific wavelength you can clearly see and identify the element. This can be transmission line or absorption line. We can use as the fingerprints to identify elements in the space. So now in the excitation, emission, and the simulated pumping or the excitation, spontaneous or the stimulated emission. Suppose your atom has the two energy level, that is the lower energy level or the ground energy level or the upper energy level. So if you supply that energy, if you supply that atom energy equals to the difference between the energy level or the delta E, that is this is E2 and this is E1. E2 minus E1 energy if you supply to this atom or this system, then the lower energy electron will jump to the higher energy level. But if you supply some less amount of energy or the higher amount of energy to this system, this electron will not make any transition. And another is the when you transit some electron to the lower to higher energy level, the electron cannot be in the higher energy level for large amount of time or for all time. This will spontaneously decay to the higher energy level to the lower energy level and emit some photon. And another way is if you supply a photon to the higher energy electron in the higher energy level, then the photon with the energy of delta E, that is E2 minus E1, and then this photon will be also come out, and also one electron will be one another photon will be come out due to the transition of upper energy level to lower energy level. This is known as the stimulated emission. Because atoms only absorb the photons with specific energy, the upward transition can produce a pattern of absorption lines at specific wavelength. And the emission line transitions are the downward transitions which produce unique pattern of emission line. And the energy level of molecules are mainly due to the vibration level and the rotational energy level. Molecules of additional energy levels, thus the spectral lines, because they can vibrate and they rotate other than only making transition from the ground state to higher state. The large number of vibrational and the rotational energy levels can make spectra of molecule very complex. Many of these molecular transitions lie in the infrared part of the spectrum. Now, this was our preliminary understanding of the emission and the absorption process, and the fingerprint, the spectral fingerprint we observe in within spectra. So we know the if we break light or the disperse light through this prism, we will get some continuous spectra. And if we have some hot cloud of gas and disperse it through the prism, we will get the spectral line corresponding to the composition of this gas. And for the absorption line spectrum, if we have we have the source, and between the source and the prism we place a cold gas, and then the prism disperse the light and we get the absorption line spectrum. So now, how does the light tell us about the temperature of planets or the star? All the objects emit the thermal radiation, whether this is star, planets, you and me. So an object's thermal radiation spectrum depends only on the one property, that is the temperature. Wind's law allows us to measure temperature of the distant object. I have to. Sorry. So properties of thermal radiation are the hotter objects emit more light per unit area at all frequency. The hotter objects emit photons with higher average energy. Here is the Planck's blackbody law, where you can see the hotter object have the lower wavelength, that is the higher frequency, and hotter objects emit more light per unit area at all frequency, and the hotter objects emit photon with higher average energy. There is the Wind's law, that is the lambda T is equal to 3 × 10 to the power minus 3, and the in SI unit, and the Stephens-Boltzmann law is the flux is equals to sigma T to the power 4. Flux per unit area is equals to flux is equals to sigma T to the power 4. So what are the until now we have covered what are the three basic types of the spectra, that is the continuous spectra, emission spectra, and the absorption spectrum. So how does the light tell us about the composition of spectra? Each atom has a unique fingerprint. We can determine which atom are made of which by looking at the fingerprint in the spectrum. So light tell us the temperature of the planets and the stars. How does light tell us about the temperature of planets and stars? Most of the objects emit continuous spectrum that depends on the temperature. The spectrum of the thermal radiation tells us about the object's temperature. The peak wavelength determines the temperature according to Wien's law. The flux determines the temperature according to Stephen's law. Now there is the idea of Doppler effect. So Doppler effect, as we know, when something comes to us, suppose there is a train. Doppler effect we all studied in class 11, 12. That is when suppose there is a train and the train is coming towards us. The train is blowing horn, and it is coming towards us. Then you will heard the high pitched sound, and if you are standing here and the train is going away from you, then you will heard the sound that is at the lower pitched. So same thing occurs when some object moves towards you and some object recedes from you. So you can think of it, the objects are sending some light or some ball towards you. That is some object is sending some ball towards you. That ball is photon. So that ball is photon or the light particle. When this object is moving towards you, you receive that photon more frequently. But when this object is receding from you, then there is you are not receiving that photon particles frequently from the object. So when some object is moving toward you, the frequency of receiving get increases, or the frequency increases means the wavelength decreases. And when the object is receding from you, then you are detecting signal less frequent, so your wavelength gets increases, or you are seeing the redshift. So sound or light moving towards you becomes shorter in wavelength, and the sound or light moving away from you becomes longer in wavelength. So this phenomena is called the Doppler effect or the Doppler shift. So suppose an object has some line in a spectrum. If this object moves away from you, then your spectrum will be redshifted. That is spectrum will be redshifted. That is on the red zone. That is the wavelength of the object. This is the wavelength. Wavelength of the each lines will increase. Each emission lines will increases. And if the object is moving very faster, then this line will be moving very far from the lab spectrum. But if the object is moving towards you, then this line will be coming towards you. That is this will be blue shifted, or the wavelength decreases. And if a object is moving towards you very fast speed, then the line will be more closer to you. So this generally measured the Doppler shift of the line to measure the velocity of the object. So Doppler shift tells us only about the part of object's motion towards you. Suppose you have a object, it is moving away from you. Then on the joining line and this moving away it is moving away along the line joining you and those object. So you will now you can detect this object is redshifted from you. But if you have any the object 3 which is going at this direction, this is not along the line of the joining that object and the earth. So the direction of this some theta direction or the cos theta part of it, you can detect only the Doppler shift along this direction. The amount of blue shift or the red shift tell us about the object speed towards us or the away from us. So in this figure also you can see, suppose you have you are sitting in the earth and another object is moving along this direction. So in this direction you will not detect any red shift or blue shift, because this velocity component have no direction along this along the u and the object's axis or the object's line. Now suppose there is an object in the sky, that object name is quasar, and there is an hydrogen gas cloud between you and the object, and you are between you and this object, and you are seeing the spectrum of the source. Now if the dash gas cloud is the cold gas cloud, then some the light that is coming from the quasar, some light will be get absorbed by this quasar, and you will see the absorption lines in the quasar spectrum. So now you can see this thing also from the shift, how shift of that line from the left frame, you can determine the velocity of the cold gas cloud. And also if you have the emission, if the gas cloud it's a warm gas cloud between you and the object, then you can see the emission line from the gas cloud. So absorption and emission line can tell us about the temperature of the gas cloud, and the shift give us indication about the velocity of that gas cloud. Also now, how does the light tell us about the rotation rate of the object? Different Doppler shift arises from different sides of rotating object spread out to its spectral lines. Spectrum of the rotating object is as spectral lines is wider when object rotates faster. Suppose there is a star, uh, some part of it is coming towards you, then the spectral line emitted from this part will be blue shifted, uh, and the spectrum of light coming from away from you will be red shifted. So this thing, the spectral line, it gets broadened, this or the spectral profile gets broadened. So what we learned today, how does the light tell us about the speed of object? The Doppler effect tells us about how first an object is moving toward an away from us. We know about the blue shift and the red shift. Object moving towards us are blue shifted, and the object receding from us or the going out moving away from us are getting red shifted. So also light tell us about the rotation rate of the object. The width of object spectral line tell us about how fast it is rotating. So in the universe, we or the in the sky, we want to measure three different properties of the object. What is the object composition? So that we measure from the spectrum, and the temperature also, that is measured from the Wien's law, and the velocity, that is measured using the Doppler shift. So today this closes our class. Thank you.